repository, so people who are not able to hear today's lecture can also go through it and hear it later on. So just to brief about the award, the international the Kaur Legacy Award is given by the Kaur Family Trust, which is managed by the family of late Professor Pradyuman Kaur, who, as all of us know, has been the father of India's National Fusion Program. The Kaur Legacy Award is given annually to a scientist between the age of 45 to 55 years. The award constitutes an engraved plaque and a cash prize of US $5,000. So till date, we have 6 winners, including Professor Sari. The award was initiated in 2018. Professor Amita Das from now currently in IIT Delhi, at that time IPR Gandhinagar, was the inaugural winner of this award. And then thereafter we had awards in 2019, 20, 22 and 23. 21, I think there was a COVID period, we could not award it. And I'll hand it over to Professor Sari by first of all introducing him to the audience. Professor Sari is a professor of physics at Queen's University, Belfast, United Kingdom, and has authored over 120 peer-reviewed publications in the field of high-temperature plasma physics and applications, where his group has obtained several landmark results, including the first generation of an electron-positron plasma, the first detection of non-classical radiation reaction in the field of a laser, and the first laser-driven generation of high-quality and high-energy positron beams. Professor Sari is an organizer of several international conferences. He is one of the leaders of the Eupraxia facility, and he's a member of several international strategy groups and steering committees on particle accelerations. So we all look forward to a very enchanting lecture from you, Professor Sari. I hand over the dais to you. It's all yours now.
All right. Thank you very much. So I'll try to share my screen. Let me know if you can see it okay, and if you can hear me okay.
Professor Sari, I think your voice...
Yeah, can you hear me?
Professor Sari, are you muted?
No. No, hang on.
I think you're muted. Mrs. Kaur is here. So, ma'am, would you want to say a few words before Professor Sari starts?
Sorry. Of course.
Hello?
I think she's muted.
Audible. Okay, fine. Then it's fine. Okay. Professor Sari, I think there's some technical issues on our end. We will take care of it.
Okay.
Mrs. Kaur, if you want to speak, you can speak.
Yeah. Can you hear me now?
Yeah.
Yeah. Okay. I want to, especially thank Professor Narayanan, Professor Das, and Professor Gianluca Sari, who have arranged for this lecture, which is in honor of Professor Kaur. And Professor Sari is the first, he's a winner of Kaur Legacy Award this year. And it is such a nice homage to my husband, who was an avid academician. So I wish PSSI a great success with the lecture series that they are trying to target and want the science and technology to reach far and wide. And with this, I think I will not take too much of your time and wish you a great start. Thank you.
Thank you, ma'am. And Professor Sari, I can. Sorry to interrupt now, Professor. Thank you.
No, that's okay. Thank you very much, and hope you can hear me okay, and you can see the slides. Okay, so today I'll try to give a brief introduction to particle accelerators based on plasmas, and I will outline some of the many applications that you can explore with these particular machines. And I'll say where we stand today and what are the future directions in this work. So this is in honor and in memory of Professor Cow, which was one of the trailblazer in plasma physics of the last few years. It has been an influential and inspiring scientist in plasma physics research. He produced fundamental. He gave fundamental contributions to the knowledge of these plasmas, laid the foundations for plasma-based fusion studies. So I'm honored and delighted to be the recipient of such a prestigious award. And in this lecture, I will try my best to follow on such a strong and humbling legacy and discuss some of results on plasma-based particle accelerators. So as an introduction, so these are the main topics that I'm going to cover. So I will talk a little bit about the basics of wake field acceleration, how it works, what is the current performance, and what is expected in the near future. And then I'll give some examples of how these electron beams from wake field can be used, for instance, to generate secondary light sources, X-rays and gamma rays, how we can use these accelerators to study fundamental physics, such as the strong field limit of quantum electrodynamics, but also how these accelerators can be used to study, can be applied in areas that are far from physics. So for instance, there's a lot of work now in using these electron beams to study biology and response of biological cells to radiation, which is of extreme importance for cancer therapy, for instance. So this is of course, this is not only my work, but I'm lucky enough to have a very large group of talented and enthusiastic young researchers at the postdoctoral level and also as PhD students. So these are the people that have contributed the most to the work that I'm going to present. And of course, in physics, in science in general, you can never work in isolation. You always have to engage with the international community and build links and bridges with other researchers worldwide. So the work that I'm going to present is is the result of large collaborations, which mainly so far include members from Europe or United States, but we're always more than happy to extend our collaboration network and work with people from all over the world. So why do we study these accelerators? So one thing to bear in mind is that high-powered lasers, since their start effectively, which was the advent of chirp pulse amplification, which won the Nobel Prize in 2018, there has been blossoming of high-powered laser all over the world with peak powers that now are in the range of the petawatt, but even exceeding the petawatt, the multi-petawatt, with the current record held by the Extreme Light Infrastructure with 10 petawatt being demonstrated. So as you can see, it's a capillary distribution all over the world. So not only Europe, US, but also Asia, and the Middle East, and so on. So there is a lot of interest worldwide in these, and a lot of investment worldwide on these high-powered lasers and how to use them for fundamental science, but also applications. So I will start by giving a little bit of an introduction to the physics of laser wake field accelerators. And with a first disclaimer, there is also beam-driven wake field acceleration, which is similar in some aspects, but different in others. I don't have time to cover both, but bear in mind that you can drive these accelerators not only using lasers, but also using particle beams. Okay, if you use particle beams, that's called beam-driven acceleration. But today we'll focus on laser-driven. acceleration. So how does it work? So effectively, in simplistic terms, what you do is you focus a high-powered laser in a gas target, and under certain conditions, this laser excites waves in the plasma at the wake, so behind the laser. That's why it's called wake field acceleration. These waves can have extremely strong electric fields in the region of hundreds of gigavolt per meter. So if you are able to place particles close to these electric fields, you can accelerate them to very high energies in a very short distance. Okay, for instance, if you want to accelerate an electron up to 1 GeV, that takes only 1 centimeter of plasma. If you want to use a conventional accelerator, that will take 100 meters. Okay. So these plasma accelerators are extremely powerful in the sense that they're able to sustain extremely high electric fields, much higher than solid state accelerators, and therefore are able to shrink, to compress an accelerator that will be 100 meters down to millimeters or centimeters. So how does it work? Okay, so you all know the Lorentz force. You have an electric and magnetic component. If the charged particle is slow, so it has a speed that is much less than the speed of light, is non-relativistic, then you can neglect the magnetic part, and the electron simply oscillates in phase with the electromagnetic wave. So nothing really happens. However, if the speed of the electron starts to become close to the speed of light, you need to take into account the magnetic contribution. In this case, the electron not only oscillates in the electric field, but also creates some sort of figure of eight motion because of the coupling with the magnetic field. So if the intensity is sufficient, then these electrons can be pushed away from the region of high intensity of the field, pushed to the side. And this force is called the Ponderomotive force. And as you can see, it scales to the gradient of the electric field square. Okay, I hope you can see the laser pointer here. Okay, so what happens? So the laser arrives into the gas, the electrons are pushed outward, the ions, as you know, are much heavier, so they don't really have time to move on this time scale, so they can be considered as immobile background. So once the electrons have been pushed out, they will then feel the attractive force of the ions which have been left behind, and they will call back. When they call back, you create a very strong region of electric field on the back, which has a longitudinal component. Okay, that's important. It has a component in the forward direction. This is the field that effectively accelerates the electrons. Okay, so this is how it will look in a simulation. Okay, so you see the electron density. This is the laser here. The electrons are pushed out and then they collapse back onto the back. You have a strong region of electrons here that create a very strong electric field. So if you have a particle here, it gets a negative particle like an electron, it gets accelerated forward. And interestingly, this has been recently observed directly in an experiment. Okay, so this is an actual experimental snapshot of the wake field distribution. Okay, and you basically see that it reproduces very precisely the electric field distribution that you expect from calculations or simulations. Okay. There are a couple of things that you need to consider, of course. One is that when you focus a laser beam, then it will start to diffract again. And this will limit the acceleration length that you can achieve because the laser will lose intensity very quickly, okay, via diffraction. However, if you're in a plasma, the plasma can act as an active lens and effectively self-focus the laser, okay? So even though the laser will try to diffract away, the plasma will keep it constantly focused, creating a very long region of constant intensity, which is what you need to drive your accelerator, okay? There are some limits in this acceleration, and the two main ones are dephasing and depletion. The phasing is usually the one that comes first, the most important. So basically, when you start to accelerate using these electrons, the electrons will go at the speed of light or very close to the speed of light, but the laser will go a little bit slower, and it will go slower because it goes at the speed of light in the medium, which has a refractive index. So effectively, the accelerating structure is a little bit slower than the electrons. After a while, the electrons will get out of phase. When they get out of phase, you don't accelerate them anymore. The distance over this happens is called the dephasing length, and it basically sets the limit, the size of your accelerator. So some results, some typical results. So what are the characteristics of these electron beams that you can get? So the highest energy ever recorded was obtained at Berkeley 4 or 5 years ago, where they were able to get up to 8 GeV in 20 centimeter of plasma. Okay, so an average acceleration gradient of 40 gigavolt per meter, which is orders of magnitude higher than what you would get in a conventional accelerator. Okay, so an 8 GeV electron beam in a conventional accelerator will be a kilometer-long machine. This was done in 20 centimeters. Other characteristics, these electrons are really, really short in time. So they usually last a few femtoseconds, which is crucial for a lot of applications that we will discuss. They can have very narrow energy spread, and recently we obtained even 1% or less than 1% energy spread. And this is very important, for instance, to drive secondary sources such as a free electron laser, which has been demonstrated this year, a free electron laser driven by plasma. And they usually have very high charge. Okay, each electron beam has usually picocoulomb up to nanocoulomb charge. So these are very interesting electron beams. Another thing that we have introduced, especially my group and the group at Imperial College London, is to use artificial intelligence to optimize and characterize these accelerators. So okay, now we have a full suite of AI models and methods for these machines to self-optimize and also to predict the response of these accelerators. Okay, and there are some publications here that you can check if you're interested on that. But it seems these particular accelerators are suited to be self-optimized and self-running effectively using AI models. So in Europe, at least, this is now a central area of research also for conventional accelerators. So CERN has asked us to create, so these are the groups involved in this, the particle physics strategy for Europe. And these are the main points of particle physics in general. And as you can see now, in the main points, you have laser plasma acceleration techniques highlighted. Okay, so this is now considered a central area of research, not only for us, for the plasma community, but also for conventional accelerators and particle physics community. For example, we recently proposed a plasma accelerator facility called Eupraxia. So Eupraxia will be the first facility, accelerator facility based on plasmas, and this will be based in Europe. So this was recently included in the roadmap of the European Union for the flagship facilities in physics. So we published a conceptual design report of the whole machine, is 650 pages. And we are now preparing the technical design report, and we have started construction. So this is not just for, what I'm trying to say here is that this is not just a plasma physics project in a sense. It's a scientific project in general, which includes material science, particle physicists, accelerator physicists, biologists, and so on. So in summary, just for this first part, laser plasma accelerators have several great advantages. One is that they are much shorter than a conventional accelerator, centimeter compared to kilometers. And this is thanks to the much higher electric fields that they're able to sustain. We don't reach yet the 100 GeV level, but we are working on it. The number of electrons we produced are similar. And another interesting thing is that they give electron beams which are super, super short, of the order of a few femtoseconds. So you can probe materials, but also biological response at novel timescales. Okay, so once you have these electron beams, what do you do with them? Okay, one possibility is to drive light sources. Okay, so to generate light, X-rays or gamma rays. There are many different schemes. I'm going to focus on two main ones. One is the so-called Betatron radiation. Betatron radiation is very interesting because it's intrinsic of the accelerator. You don't really need to do anything, okay? Once the electrons are accelerated in the cavity, they also produce this radiation. And how does it work? Basically, the idea is that if an electron is a little bit off axis compared to the main accelerator axis, then it will accelerate forward, but it will also start to oscillate up and down. And as you know, an accelerated particle emits radiation. Okay, so this creates an X-ray beam which has very high spatial resolution of the order of a few micron, and it's spatially coherent. That's the important thing. Okay, so the spatial coherence is very useful because you can use these beams to do what is called phase contrast imaging. Okay, so this is an X-ray imaging technique that doesn't rely on absorption, but relies on the difference, on the contrast in phase. And here are some examples of images that we took using this technique. This was mainly in collaboration with Imperial College. One of the main results is this live embryo of a mouse that we were able to image using a plasma-based Betatron source. And we were also able to do tomography. Okay, so this is a full 3D imaging of this mouse embryo using this technique. And as you can see, the level of detail is incredible. You can have micron scale resolution. You can look in depth because you have high energy X-rays. And also the amount of dose deposited on the sample is very low because you're not relying on absorption, you're relying on phase contrast. So it's usually of the order of the centigrade. So you don't even affect the sample. Okay, so this is very important if you want to do biological imaging. Okay, so this is one example. Another, if you want to go up in energy, if you want to go to the MeV range, which is important for nuclear studies, for instance, you can use what is called Compton scattering. So in this case, the electrons are hit by a second laser, and the electrons oscillate in the laser field and produce radiation which can be up to tens of MeV. Okay, and currently this is the scheme that provides the highest brightness of gamma rays in the 10-20 MeV range, which is very important for nuclear studies because most of the nuclear resonances happen in this sort of energy. Okay, so as an example, we tried to do some imaging of this. So we took some grids. Okay, so these are resolution grids with like 200 micron features. We put them behind 5 centimeter of lead, and then we shot them with a Compton beam from the plasma accelerator and took an image of it. And this is the image that you got out of it. So you see that you can get very clean, high resolution images even behind walls of a few centimeters of lead. Okay, this is important for strategic reasons. Okay, for the detection of uranium or so on, for national security. And if you compare the original object with the image that we took, you see that there is complete one-to-one correspondence with very high resolution and very high contrast. Okay, so this is quite useful to do imaging of stuff behind thick walls or enclosures. Okay, another thing that you can do, which is quite more on a fundamental side, is to study fundamental physics. Okay, one aspect of it is to study quantum electrodynamics. in the so-called strong field regime. So what do we mean by that? Okay, so QED is the best theory that we have to describe electromagnetic interactions. It is quantum, it obeys special relativity. But how does it work? Okay, so let's assume classically, okay, let's assume that you have an electric field, an oscillating electric field, an electron arrives. Classically, nothing really happens in the sense that classically the electron emits radiation constantly, okay? And this radiation is Doppler shifted, but the electron doesn't lose much energy during this process, okay? The electron energy loss due to radiation can be treated perturbatively, okay? So this is a clear picture. We know how it works. That's the classical idea. However, what if you go to very extreme, very high fields? Then, in this case, you need to use quantum mechanics. And in this case, you need to be careful because, of course, in quantum mechanics, there are no fields. Everything is particles. So now you have a background of laser photons. Then the electron arrives, and a few surprising things actually happen. The first is that the electron doesn't necessarily emit, okay? So the electron can actually propagate for some time without emitting at all. There is only a certain probability that the electron will emit a photon. Okay, so you don't have a continuous energy loss, but you have a discretized energy loss. Whenever the electron emits, it emits a photon. Okay, so it emits a high energy particle, and it's deflected because of that. Then another thing that you have to take into account is that the electron might lose a lot of its energy, even during a single emission. So electron recoil is important and you have to take it into account. Another thing that can happen is that the emitting photon can decide to generate an electron-positron pair. Okay, so you can have generation of secondary particles, and this can continue forward in a cascade. Okay, of course, these are all things that don't happen classically. So the idea is that how do you correctly model all these different effects? So stochastic emission, high energy losses, and the possibility of pair production. These are modeled in quantum electrodynamics, okay? So via nonlinear Compton scattering and Breit-Wheeler pair production, okay? So these are the Feynman diagrams, if you're interested, of these two events. So you need to be careful now, because now the electron is losing a lot of its energy during the emission of radiation. So while the electron is accelerated by a field, it also loses energy through radiation or emission of photons. So the Lorentz force, of course, does not have that, does not include that. Okay? The Lorentz force assumes that the electron energy remains constant. So there have been attempts to extend the Lorentz force to include radiative losses. The first was the Lorentz-Abraham-Dirac equation, which is here, which includes a damping force, but it has some issues, okay? It has issues with renormalization, and also it has a very big issue that it has runaway solutions, which are not physical, okay? You see here that even if you put the external field equal to 0, there is still a solution where the electron will spontaneously accelerate exponentially, okay, which of course is non-physical. A solution to that is was given with the Landau-Lifshitz equation, which now has no runaway solutions, has no problems, is valid in classical relativity, but it's only valid up to a certain field, the so-called critical field or Schwinger field. Okay, so how do we access the Schwinger field? So this is where we stand at the moment. Okay, so this is the energy of the electron or the gamma factor of the electron, and this is the laser intensity normalized. Okay, so 10 to the 0 corresponds to a laser intensity of 10 to the 18. This chi equal to 1 represents the Schwinger field. Okay, so anything above this is a strong field QED. Okay, so the first experiment in this area was performed in SLAC in the 90s, where they reach around 20% of this critical field. Recently, we did a series of experiments in RAL, in the Rutherford Appleton Laboratory, where we were able to reach again a similar value of the quantum parameter. And we were able to see quantum effects in radiation reaction and study pair production. And we now have a series of experiments planned. One, Facet 2 at SLAC, LAXI at the UXFEL in Hamburg, and ELI at the Extreme Light Infrastructure, where we are planning to go above the Schwinger field and study physics above the Schwinger field. Okay, I'll skip that, it's not too important. Yeah, maybe I'll skip that as well. So one example of these experiments is the LAXI experiment, so the Laser und XFEL experiment, which is an experimental program that we have proposed to the European XFEL. It includes more than 100 scientists from 26 institutions across Europe. The technical design report is now available on the archive. But basically the idea is to study these Schwinger field effects and study the physics that is above the Schwinger field, where, to be honest, no clear first principle theory is present yet. Okay, so this is literally discovery science at the frontier of what we know. Okay, so what are the moonshots? Okay, moonshots, you have to think of what is the real target of the long term. Okay, what do you really want to do? Okay, one thing that we want to study is the so-called photon-photon scattering. Okay, so sorry. So this is an event which has a very, very small cross-section. It classically does not exist. Okay, classically electromagnetic radiation should not scatter from each other because they don't carry charge. However, if you include quantum fluctuations in vacuum, you see that even two photons traveling close to each other should definitely scatter away because of the mediation of the virtual particles in vacuum. Okay, so of course this is a very rare event, and there are some indirect studies that anyway are very far, can only set very loose limits on this cross section, 10 to the 6, 10 to the 10 times higher. However, if you use very high intensity lasers, and we are preparing experiments in this kind, for instance, 2 10 petawatt lasers, you see that in order to generate one photon scattering event, you only need 10 to the 4 shots. Okay, so if you have a shot every minute, this is 7 days of data acquisition. If it work at 1 Hertz, this now takes only 3 hours. Okay, so one thing that we're planning to do is to provide the first experimental measurement of the cross-section of photon-photon scattering. Another thing that we are planning to do, but this is more far in the future, is to study QED at extremely high intensities. Okay, so there is a conjecture called the Ritus-Narozhny conjecture that says that when you start to get to extremely high intensities, QED starts to become a fully non-perturbative theory, basically meaning that every process, QED process, has the same even more higher probabilities to happen. So you cannot apply perturbative truncations, but every phenomenon occurs at the same time. This is quite interesting because basically this tells you that at these extreme intensities, even the concept of electrons and photons as individual particles will completely lose its meanings. Okay, so it's not really clear. We need a completely new physics description at these fields. There are caveats, of course, there are experimental issues and so on. Don't have time to talk about it, but this is the idea, to get to this sort of intensity, which is about 10 to the 23, 10 to the 24 watts per centimeter square, when basically QED starts to become exactly like QCD, okay? And in this case, there's completely new physics to be observed, okay? Okay. Another thing we are planning to do is to use these plasma-based accelerators to produce muons. Muons are particles, are leptons, like electrons, but are heavier. They're around 200 times heavier than an electron, so they are 200 times squared harder to produce. but they are very useful for a very a long series of applications, and mostly because a muon is much more can penetrate much better in matter, so you can provide radiographies or muographies, as they call them, of extremely thick objects and extremely large objects, where electrons and photons would not be able to do that. You might have heard about the use of muon radiography to, for instance, to probe pyramids in Egypt, where they were able, using cosmic muons, to detect hidden chambers in a pyramid in Egypt. The interesting thing is that if you use a 10 petawatt laser to drive your plasma accelerator, you can get very high energy and very high charge electron beams. And if you shoot these electron beams onto a solid target, you can get a significant amount of muons. Okay, so what do you do with these muons? One thing, for instance, you can do radiographies of thick objects. So this, for example, is a simulated radiography that we did for national security studies, but we can show around, it's published anyway. And this is, for instance, the detection of 2 uranium blocks. You can see clearly the shadows here, enclosed in a 2 centimeter lead box. Okay, so you see how clearly you can detect them, and this, of course, has very important implications. Okay, so we did a first experiment at the extreme light infrastructure, and we were able to detect some of these muons. So this is quite interesting for didactic reasons, if there are students or postdocs. So this was the one image, let's say, that we got onto the detector. You see that there is a mess, okay? A lot of different particles, a lot of different tracks. It's very hard to say what is what. However, if you consider that each particle has its own fingerprint, okay? So it has a certain size of the track, a certain thickness of the track, a certain amount of energy deposited. It can only arrive at a certain time. You see that if you apply all these filters progressively, you can remove everything that is not a muon, okay? And by doing that, you see that you end up with only a few tracks. Then you can do some more selection. Basically, for instance, if you look at the direction of these tracks, you know that they're not coming from the interaction. This track is too thick to be a muon, so you see that you can isolate potential candidates, even when you start from something that looks like this, okay? So by filtering and applying the right constraints to isolate the right particles, you see that you get the right, in this case, 3 muons per shot, but we can do more than that, okay, just as an example. Okay, now, the last thing I want to show you, just to give you basically a general overview of things we can do with plasma physics. I want to give you an example of what you can do in radiobiology, okay? So radiobiology basically tells you how living tissue reacts to external radiation, okay? And if you look at that, there are several scales involved, okay? So there is a physical response, so the radiation arrives, ionizes the water, creates radicals, and so on. This usually happens on a femtosecond timescale. Then you have all the chemistry involved, and this chemistry goes from picoseconds to seconds, and this is where you start to trigger DNA damage and so on. And then there is the biological response, which is very slow, okay, and then happens in the regions of hours all the way to years, okay? But if you think about it, what the radiation really does only happens in this femtosecond scale, okay? After that, it's all a cascade of events inside the cell, but the radiation has passed already, okay? So an important, very important aspect of radiobiology, especially for cancer treatment, for radiotherapy, is to basically study the femtosecond scale radiation. And this, if you remember, one aspect of these plasma accelerators is that they give femtosecond electron beams. So you can clearly probe the early response of cells to radiation. And this is extremely important for cancer research. So we did a series of experiments and without going into too much detail, we see already some very interesting effects. So these are examples of cells irradiated, and you see the number of damages. So these bright dots are the damages induced in the cell. One thing that we see, and we have some ideas as to why this is happening, but this needs further research, is that the cells are more sensitive. So with the same amount of dose, if the dose is delivered within femtoseconds, then you're more efficient at killing cells. And also, which is extremely important, you don't see radioresistance from the tumor. Okay, so basically you see that the tumors start to behave exactly the same way as healthy tissue, which is extremely useful for cancer therapy. An interesting thing that we see is that these effects are triggered only at femtoseconds. So if you move to picosecond irradiations, these effects disappear. So it's something that is intrinsic to the femtosecond scale, and plasma-based accelerators are the ideal tool to study these effects, which, to my opinion, can have a strong effect on the future of radiotherapy and cancer research in general. So concluding, there's a lot. Okay, I understand this is a lot of stuff, but I also want you to realize that this is only one aspect of a much wider range of science and applications that you can do with plasma accelerators. And this is mainly driven by the fact that you can have ultra short, very high current and high energy electron beams in an accelerator that you can now fit in a room. Okay, so every university, every hospital, every research center can do their own research. There is a lot of interest internationally. There are strategy groups, there are international facilities being built. So this is the right time to be in this kind of research. You can use this research to do both applied and fundamental science. And I gave you some examples of applied work in X-rays, gamma rays, muons, radiobiology, and so on. But you can also do very fundamental science, for instance, a strong field QED. And with the new next generation of 10 petawatt class lasers, which are coming up online as we speak, we will be able to access regimes of physics where there is not even a theory yet, a completely new, uncharted territory. Okay, and this is all driven by the basic understanding and the fundamental understanding of plasma physics that pioneers like Professor Kao inaugurated. So thank you very much for your attention. I really appreciate it. And I'm more than happy to take any questions that you might have.
Thank you, Professor Sari, for that very informative and exciting talk. I would ask the audience to raise their hands for any questions, and then we can coordinate. Anybody from the audience who would like to ask any questions?
It was all clear.
I think, I think yes, Sarvesh. Somebody has raised Sarvesh, I think.
Yes, Dr. Ramesh, can you hear me?
Yeah.
Yes, Sarvesh, please.
Oh, thank you, Dr. Sari. It's a very wonderful, great lecture. And I am from accelerator background. I really would like to know like you described about the beam wake field also, that disclaimer you said. And you explained very nicely laser wake field plasma acceleration. So in this beam wake field, if you can summarize in a few lines, what is the latest status? Is it better than the laser wake field scenario right now internationally? or are we still dependent upon like awake scheme at the sun, like beam driven type?
Yeah, no, this is a great question, and neither are better or worse. They have their advantages and disadvantages. Okay, so a beam-driven scenario is more advantageous because now you have a beam to drive the wake field, not a laser anymore. So for instance, you don't have many problems in terms of depletion and dephasing. So for instance, you can create much longer accelerators. So beam-driven accelerators now can be 1 meter or even 10 meter long. The issue they have is that usually they have lower gradients. And also in my opinion, one limitation is that you have to rely on a very high energy beam already to start. So you need to have an accelerator to provide you the driver to drive the plasma accelerator. So you don't really get rid of the size and cost of a conventional accelerator because you still need the conventional accelerator to give you the beam to drive the wake field in the plasma. That said, there have been some really exciting results in this area. For instance, you can check the AWAKE collaboration, which is an experiment in CERN, where they use the 500 GeV proton beam from CERN to drive a wake field. And they're getting very interesting results in this direction. Let's say, in summary, if you want to go to extremely high energies, like hundreds of GeV or even the TeV, the feeling is that you need a beam-driven configuration for a lot of reasons. But if you want to have smaller hundreds of MeV, GeV scale accelerators, which are compact that then can be used for applications, then the laser-driven is still the favored option. And I hope that answers.
Yes, very well. And just few more words on the quality of the beam accelerator. Is it means if you compare both of them, is it better in beam or is it better in laser side?
Not necessarily. The thing that really dictates the quality of the beam coming out, for instance, in terms of slice emittance and so on and so forth, is not the structure of the wake field, but it's how you inject the particles in the wake field. So in principle, you want to have a cold injection, so you have to have extremely cold, very small temperature populations of electrons, which are injected all in the same position, in which case you can generate very high quality beams. So the problem of injection is common to laser wake field and beam driven wake field. So it doesn't really depend on the type of wake field that you choose. It depends on how well you're able to inject the electrons.
Okay, thank you very much. Yeah.
Thank you.
Thank you, Sarvesh. Thank you, Sarvesh. I think Senthil has raised his hand.
Yeah.
Senthil.
Yeah, is it audible?
Yeah, it is
Yeah.
audible. It is audible.
Yeah, actually, I want Professor's comment on the modeling of plasma. The plasma in many of the devices, effect of plasma on the beam quality and the performance makes a lot of difference. Would like to comment on what kind of modeling, what kind of software tools will be more apt for having a better experimental matchings?
Yeah. So at the moment, these plasmas are modeled using particle in cell simulations, which are, as you know, any simulation, any numerical model is an approximation because it doesn't take everything into account. It has some simplifications in it. However, it is now reached a point where the match with experimental results is extremely good, and it's down to experimental uncertainties. In order to do that, you need to run with extremely high resolution, so you really need to have access to supercomputing capabilities. For example, just to give you an example, a normal cluster, university-sized cluster, if you want to simulate a picosecond of interaction, that will take a few days of computer time. So it requires a lot of capacity, computer capacity. But in terms of modeling, we are now in a position where the matching can be reached within experimental uncertainties, if you have enough
Uh,
time.
I'll mail you the mail ID what you have been shared. Can you share some of the application papers for the accurate modeling of plasma in particularly the software CST or something? Can you share the papers so that it will be helpful for kind of applications?
Share the papers.
Yeah, publish the open literature papers if you come
Yeah.
across anything.
Yeah. I can send, I can send some lists to the people organizing these events
Yeah.
so that they can disseminate it.
Sure.
And yeah, of course.
Sure.
Thank you.
That's definitely done. So
Okay.
yes, yeah, sure, Professor. We'll circulate it as a.
Yeah,
Uh,
absolutely. No problem.
Thank you.
Thank
Thank
you,
you very much for that. Are there any other questions regarding?
And of course, if you can't circulate my email address, I'm more than happy to take, questions offline and discussions offline. That is absolutely no problem.
Absolutely. I'll definitely do that. I'll definitely do that. In
Yeah.
fact, your web page is already shared with everybody, so I
Yeah.
presume. Sure.
Okay.
Is there any other questions from the audience here?
That was a lot, so people are probably
Yeah.
silent.
So
But-
it's a more layman question, and I think it's more for I think some of the students they may be keeping quiet. You showed that the image processing where you tried to identify the muons, right? So could you just elaborate on how you would go as this it means little bit elaboration for the student's point of view to get more clarity. Is it possible?
Not yet. I'm
Not yet.
sorry. I'm sorry.
Okay.
Yeah,
Okay.
because
Fine.
there are some safety, national security.
Absolutely. No.
Sorry.
Well.
But
Yeah.
we
Sure.
will publish what we can. So this will come up with
Sure.
some description, but not everything. I'm sorry.
Yeah. So no, it's all right. No, absolutely no problem. In case,
Mm.
in fact, as and when it publishes, I think it will be nice if we can, whatever the students can, maybe
Yeah,
they will be getting
absolutely.
more.
Yeah,
More
absolutely. Absolutely.
Sure.
Absolutely.
Thanks for that. And any more else from the audience? Anybody who wants still to ask any questions?
Yeah.
If not, thank you, Professor Sari, for coming and giving this talk. First of all, and also congratulations for this 2024 Core Legacy Award.
Yeah.
And
Thank
we
you.
hope we'll get to see more laurels. You're getting more laurels in the future and more such high-end research activities from your end. Thank you very much.
It was a
And on
pleasure.
behalf of PSSI, so anytime you come over to India, we will be more than happy to host you.
That's great. Thank you very much. Thank you. And have a great day.
Sure. Thank you. Bye.
Bye. Bye.
Thank you all for in the audience and for coming and hearing this. And we hope we will have the second lecture series very soon announced. Please wait by for the news. And I hope I don't have this technical issue next time. I'm sorry for that initial technical issue. Okay, bye. Good. And thank you, ma'am, for your presence. Mrs. Cow, thank you very much for your presence and staying for the entire period.